So yeah, my name is William Carroll, and today I'm going to be talking about sensible concurrency in Elixir. But before jumping in, I just want to talk about briefly why I find this topic so interesting. So currently I work at a startup in New York called Urbant. It stands for Urban Intelligence, and we're a functional programming shop, and we use Elixir on the back end, Elm on the front end. We prefer Elixir in all aspects, syntax included. But we do a lot of data ingestion for New York City. So there's a lot of open data, and we're ingesting hundreds of thousands of records per week, and we have billions of data points. So for us, performance is not really a luxury. It's sort of a requirement. So our day-to-day code needs to leverage concurrency to sort of relieve and smooth out a lot of bottlenecks that you'll get when you're dealing with mountains of data. So today's talk, I just want to take a look at concurrency at different points along the spectrum. Some examples might be low-hanging fruits. Others are meant to be more practical and real-world use cases. And then I want to showcase some tooling along the way, stuff that we use daily to aid our decision-making. And then along the way, if I wax poetically about Elixir, I guess that's why we're all here anyways, so don't mind me. So quickly to just clarify some of the terminology I'll be using. So concurrency, concurrent programming is going to be an umbrella term. I'm going to be focusing on basically parallel computing. There's complications involved in distributed programming because you get network latency introduced, so running metrics on that is something we won't be doing today. And then I'm talking about concurrent programming in contrast to serial programming, which is that small circle, kind of lonely in the corner over there. That's just a rhetorical ploy, basically. But serial programming is going to be the stuff you'll typically find in imperative languages where procedures are executed in series, one after the other, and one procedure that's downstream from another is going to be blocked. So basically jumping in, I think when people first start talking about parallel programming, you get really excited about all the possibilities. You're going to basically solve all the world's problems by throwing a bunch of cores at your architecture, and eventually you're going to have programs that can compute extraordinarily fast. But there's this really interesting law that helps sort of describe the limitations that are in place. It's known as Amdahls Law, and he was a mainframe engineer at IBM. And he basically wanted to encourage programmers to look at the proportions of their code that are going to be executed serially, and then compare those with the proportions that are going to be executed in parallel. And he's basically trying to say that no matter how many cores you throw at your problem, you're still going to be limited by the amount of time it takes to execute the serial instructions. So if you have a block of code that takes, say, an hour to execute, 50% of the time is executing serial code, the other 50 parallel. You're going to be spending 30 minutes in serial code, and if you added, say, 2 cores, then you could get the 30 minutes of parallel processing down to 15, theoretically. As you add more, that number will start to approach 0. But even if you had a 10,000 core, supercomputer, you're still basically going to be taking 30 minutes to run your computations. So this is mildly sobering, I guess, for some. But it's kind of important to bear in mind. And I'm going to apply this to an example that hopefully is mildly current, which is the problem of factoring the product of large prime integers. So if anyone's been paying attention to the news lately, ransomware has been getting a lot of attention. And that has to deal, obviously, with the problem of encryption, which is predicated on how difficult it is to factor large prime integers. But we might have the antidote with Elixir, perhaps not. But I want to take a look at some code that will begin as serial procedures and then break that out into parallel processing and start to see what kind of performance benefits that we should expect and what we'll actually get and how to measure those. So first, just referring back to Amdahls Law, we have to take a look at the algorithm and see how much of this code is going to be executed in serial at a necessity, and how much of it can be and should be parallelized. So pretty simple implementation here. It accepts x, which is going to be the product of the two large primes. It's more generic than just large primes because now it can handle even functions. It just says, or even numbers as a optimization. It'll just filter out numbers that it won't need to try. But essentially, what we're going to do is take the range from 2 all the way up to this number and filter that list according to whether it's an even divisor into our dividend. So here is our serial portion. This is going to be our concurrency or parallelizable area. And we need to see how long it takes to compute each, which leads me to the first tool we're going to see, which is timer TC. It's from Erlang module timer. And this is a really great way to just gauge how long it takes your blocks of code to execute. We use it all the time just to quickly get a pulse for our implementations. And it returns a 2-element tuple. I think we agreed tuple was the pronunciation. So 2-element tuple, where the first element is going to be the amount of microseconds it takes for the procedure to process, which isn't exactly human readable, but here it says it takes 6.3 seconds for us to factor the product of these two large numbers. And then the second element is going to be the result of the computation. So applying this to our previous implementation, we're just going to wrap the portions that you saw in red in timer TC calls, pattern match on the results, and then there's a special function on line 42 that's going to log some of these Amdahl metrics to help us get a quick insight into how parallelizable this problem really is. And as it turns out, as a contrived example often is, 99.9% of this problem could be parallelized. That's because the serial part is pretty negligible. Most of this has to do with distributing our inputs, which is going to be the range from basically 2 to the prime number that we're trying to factor. And so we can be able to distribute that. So a quick way of doing it is to use tasks. If you guys haven't used these before, they're a pretty quick way of just spinning up processes and abstracting away the message passing and receiving loops. So what we're going to do is basically split up that range that we saw earlier and put one half of it on one core, the other half on another core. And then we're going to weight the results of both and concatenate them together. And then we're going to basically find out what kind of metrics we get in terms of speed enhancements. So before it was running at around 6 to 10 seconds in serial. And in this implementation, we end up getting basically 4 seconds, which is, I'd say, it's definitely an improvement, but it's not perfect. Which leads me to the next tool that we use all the time. This is HTOP. I'm sure many of you have used this before. But this gives us quick insights into basically how performant our code is, if it's meeting our parallel expectations. So here I've got 8 cores available to compute on, and you can see this right here. And I sorted by the amount of CPU usage. So it's great to see the beam as number 1. That is a welcome sight. And then this metric here will actually tell us what proportion of our available processors we are using. So the beam right now is using basically 1 3/4 of all 8. So this is good. We've improved. But I'd say as ambitious Elixir devs, we can and should aspire to do better. So it's time to refactor. So in this refactor, I'm basically going to take in the number of cores and spawn a single task per core dynamically. And since there were 8 cores available previously, we're going to call this function to take advantage of all 8 cores, and the algorithm won't change. And so here, the results back from timer TC are showing us that it takes 1 second to compute the product of these two large primes, which going down from 10 seconds is an order of magnitude improvement, which is fantastic. As you can see, the ordering of our result in the second element of the tuple is not guaranteed, but for this problem, it's not really an issue, and we could sort it, and sorting a 4-element list will pale in comparison to the time it takes to factor this product. So this is a pretty large success. But let's head back to HTOP and see basically, oh, and here's an alternative implementation actually, using the Flow API, if you guys aren't too familiar with it. But this is, I mean, fantastic API design. This is one of the reasons we love Elixir so much, is how off-the-shelf some of these really potent concurrency primitives are. The algorithm is almost a one-to-one to the previous one where we use stream. But heading over to HTOP, this is basically the distributed or like concurrent programmers analog to the 4th of July. All 8 cores are completely lit up, which is magnificent. With minimal effort, we have this. We have the beam basically firing on all cylinders, and so we can see our CPU usage is basically 7 3/4, which is up from 1 3/4 when we just had 2 cores operating. This is freaking sweet. I love this. So, seeing something like this, you might be inclined to say, okay, concurrency is going to solve all my problems. But surely there are limitations. For instance, this block of code here is parallelizable. The assignment of the computation to y does not depend on the thing that is upstream from it, the assignment of these values to x. So technically, these could be parallelized. The question is, should they be? Do you guys have any intuitions? No. That's like 3 of you. You're right, though. It shouldn't be. And that's basically because we know these operations are what CPUs are designed to solve extraordinarily quickly. So just a quick look into processes to sort of confirm why that intuition was maybe kind of obvious. You've heard that Erlang processes are lightweight. And you often hear this in contrast to operating system level processes. And this is true. And Erlang processes are very lightweight. But they do have overhead. Each process, when you spawn one, basically occupies 309 words of memory to include the heap, the stack, and when you copy over your scope from the origin of where you spawned the function, 309 words, which on a 64-bit system comes out to 2.5 kilobytes, is what's allocated in terms of memory overhead, versus an operating system process on a 64-bit machine will allocate 8 gigs of virtual address space. So comparing those two, it's quite clear that Erlang kind of nailed process threading. But when we want to run metrics on this simple variable assignment, we want to see what it means to allocate 309 words of memory, because we're kind of concerned with computation time at the moment. So how long does it take to spin up 2 processes and await their results? So this is without any concurrency involved. It's going to take 5 microseconds just to run this code in serial. Here's the concurrent version of this, which is quite elegant. And when we run timer_tc metrics on this, not surprisingly, we find that it takes longer than the previous example by an order of magnitude, which is kind of a hyperbolic thing to say, considering that we're dealing with microseconds. And if you step back for a second and you think that Erlang is spinning up 2 processes, copying over environments from one core to the other, and then back to aggregate the results, 50 microseconds is really a small price to pay for that kind of voodoo. Still, should not do this. You should not be doing this in your code base, obviously. I think everyone here knew that. But that doesn't mean that for other variable assignment, you won't want to use processes. And this is stuff that comes up in our day-to-day work pretty frequently. So basically, should we parallelize the serial version? I think after looking at the timer_tc metrics, the answer is quite clearly no. But it is sort of difficult to identify when we should be going concurrent and when we shouldn't be. And some of that, I think, has to deal with the way that we write code. And obviously, when you're in a code editor, you're dealing with two-dimensional space to just allocate everything. But when we read code, we're sort of parsing it line by line, which I think sort of lends a one-dimensionality to the process. So even if two expressions are computational siblings, so to speak, like the assignment of x and y, we're not going to readily see it because there's an implied hierarchy when one line comes before another line. So there's just this sort of serial nature to the way that we write code, and it sort of takes a little more of exposure to the subject to kind of develop an intuition for when we should be taking two serial statements and separating out their computation. So this is code that we use. This has been declassified, and it basically just downloads over HTTP some documents, and it's going to do a lot of things in the download and stream helper function. So that includes downloading, unzipping the file, and then sanitizing these strings because we're dealing with manually entered digitized forms. So they're quite awful. And then also just basic like decoding that's involved in coercing string numbers into actual integers, floats, etc. And this is probably, like, on average, we're dealing with data that, like, say a CSV that has 50,000 lines, sometimes 600,000 lines. So in this case, this is almost a complete analog to the variable assignment of x and y that we saw earlier and that we were kind of mocking. But that doesn't mean that every time that you have to assign to a variable that you don't want to leverage concurrency. So here we decided to take this chunk of code, wrap it in a task, and then downstream from that, await the results, put it into a flow, and ship it downstream such that we can sort of have that euphoric moment when we open HTOP and see all of our cores glowing. So just as a final note, I'd like to say that if we start to think of code instead of one-dimensional streaming it line by line and start to view it as a two-dimensional graph, it might be a little more readily apparent that the times when we should go concurrent. And to sort of illustrate this, I took the previous example and just broke up each statement and rendered it as a dependency graph. And here I think it becomes pretty clear what can be parallelized and what could run in serial. And with that, I'll just say stay vigilant, keep an eye out for things like this, and continue using Elixir because it is a fertile ground for concurrency. We really like it, so I'm closing with that, and I'll let you guys get to lunch. Thank you.